Okay, good afternoon, folks. Let's see. For the Excel equations on the last Excel video, where can I find what to put into? Same equations that you use in video 1 and 2, and the only difference is in the last lecture, used sigma changed, and you shouldn't be having any problems doing the Excel number 3. You shouldn't. You don't need any extra stuff. You have all the information to do Excel 3. Okay, let's start with today's lecture. We are on chapter 16, still chapter 16, the last part. I just want to remind you that this is week 6. Next week, next Wednesday, not this coming Wednesday, but next Wednesday, we are going to have the second midterm exam. And I want to warn you in advance, you need to be prepared. It's not going to be as easy as you have the first midterm exam. So you have to be well prepared for this exam. Anyhow, it's going to be, I think most likely, I will let you know, but at the moment, I don't know, but most likely it's going to be through chapter 18. Whatever it's we left off, like I think the first midterm was through chapter 8. Now this is going to start after it. It's not a comprehensive, but they are related. You cannot separate, the first few chapters from the rest of the textbook. The rest of the chapters we covered in the second midterm. But I will not pick questions from the chapters that you have been tested for in the first midterm exam. But there might be some terminology, some of the things that they will be used in the following chapters, which means chapter 10, 15, and 12, 15, and so forth and so on. Anyhow, your Excel is due today, and you have another Excel, which is going to be Excel number 4. It will be posted at 6 o'clock today. You can't hear me? Do I have, let's see. Okay, I raised the mic to the max. I don't know why you, is it better? Can you hear me now? Okay. It's the max. I can scream, I can speak a little bit louder. Okay. All right. Oh, okay. Okay. Is it better now? Abby, is it better? Okay, good. Okay, let's start it. So this was, we are dealing with the last part of the equation. Last part of the problem number. What did we have here? This is problem chapter 16, and this is problem we had problem number 4, part C, and so. This was confidence interval. We went through this, that, and this is problem 3, and this was problem 4. In problem 4, we had basically data thickness of the tree bark. Basically, we calculated this, and this was the how don't you guys see it? Let's see. I'll make this one.
Hi, we're going to give you an overview of using big.
Okay, should be better now. Okay. All right. So we went through this, and this was part B. We calculated that, and then we are doing now part C. Part C says, what sample size would be necessary to guarantee a margin of error of less than 3%? And 3%, 3.3 centimeters, not percent, for our 96% confidence interval. So we need to calculate this. So first of all, we need to know margin of error. Margin of error, what is the formula for that? If you recall that, that would be Z star sigma over square root of n. That is the margin of error, right? We had it from, this is when you write the confidence interval, you have x bar plus and minus d. And that's the d part is the margin of error that we had this before. But we have 96% confidence interval, so confidence level. So we want to know what the Z star is from here. So in order to do that, we have to go back to the table, and the table is going to be table C. You have this table on Canvas. Here, I'm going to show you again how to find that value. So we are looking at 96%. If you look at on the top, this is 96%. So that is the confidence level, 96%. You find that. Put that ruler next to that column. Come down all the way down here. And this is Z star, row Z star. Wherever they cross, that is 2.054. That would be the Z star for 96% confidence interval. So so from here, we say Z has 2.054. That is the Z star. Okay. And previously from this one we had, let's see, what was the sigma? Sigma was, if you recall this, look at here, sigma is 1.3. I'm going to rewrite that. Sigma is 1.3. And also, we want to know, we want to find n. N is the unknown. Okay? So the idea is I have this is margin of error. I want that margin of error, Z star, sigma over square root of n, to be less than 0.3, less than 0.3. So if that is the case, I want to know what should be my sample size, n. I want to find the value of n. It's unknown. Just plug the numbers and see what we can do. I mean, this is what we got, a Z star here. We have sigma there, put it there and solve it. 2.054, sigma is 1.3, n square root of n. We want to calculate n less than 0.3. There are two ways of solving this problem. I'm going to do both ways so you can see how to do it. But if some of you are good at algebra, you know how to do this quickly. So one way is I'm going to multiply, because I have to find the square root of n. I have to find n actually. In order to find n, I need to bring this n up to the numerator. So what I can do, I can multiply both sides by square root of n. And here, less than 0.3 square root of n. Both sides should be multiplied by square root of n. Since this is in the denominator, that's in the numerator, I can cancel that. Now I have 2.054 times 1.3 less than 0.3 square root of n. Then I can divide both sides by 0.3 because I want to isolate n here and calculate n. Again, this cancels with the numerator. So we have in the numerator. Now I have 2.054 times 1.3 divided by 0.3 less than n. Now, how do I calculate n? I have to square both sides. So I'm going to square this side. I'm going to square that side. So if I square this side, this is going to be 2.054 times 1.3 divided by 0.3 squared less than n. And if I do that, if you put it in your calculator, you get 79.22 less than n. So because n is a whole number, as I mentioned in the past, even this is 79.00001, very small decimal, always if it goes beyond what you have there, doesn't matter how small, you have to basically round it up. So in this case, if I round this up, 80 would be the one that I'm looking for. So basically, I say at least n has to be 80 in order to have marginal error of less than 0.3. Okay. The other way to solve this, because again, I want to find the value of n. N has to be in the numerator. I can flip both sides. When you flip both sides, always this inequality sign will change. When you change, the example is if you have 1/2 is less than let's say 1/3 is less than 1/2. If you flip both sides, that becomes 3 and becomes 2. So this has to change to greater than. You can see that 3 is greater than 2. So anytime when you flip anything, if it's a less than, it has to change to greater than. If it's greater than, it has to change to less than. So in this case, we are going to flip this, and that becomes square root of n, 2.054 times 1.3. And this is going to flip, and this is going to change to greater than sign, and that would be 1 over 0.3, because you're flipping everything. And again, you're going to do the same thing. You're going to multiply both sides by this number. So that means this would be 2.054 times 1.3 square root of n divided by 2.054 times 1.3 greater than 2.054 times 1.3 divided by 0.3. This cancels with that. Then you have square root of n greater than this number, 2.054 times 1.3 divided by 0.3. So you want to find n. You got to square both sides. So square root cancels with the square. So n is greater than this number. And that number is, we calculated, it is 79.22. So that means n must be greater than that. So that means at least n has to be equal to 8. If n is 80, the size that you're dealing with, definitely your margin of error for 96% confidence level is going to be less than 0.3 centimeters. Okay? Those are the kind of questions you might see in the exam, final or midterm exam. All right. Don't have questions. Let's move on to chapter 17. Okay, this is chapter 17. And chapter 17, we saw that in chapter 16, we dealt with one of the statistical inferences. That was confidence interval. In this chapter, there's another statistical inference, and we call this tests of significance. And this is very important. Definitely, you will see questions on confidence interval and significance, test of significance, in midterm exam and final exam, both of them. In the final exam, here we are doing with one sample for confidence interval and tests of significance. The final exam, after the second midterm, we're going to deal with two samples. And the formula is going to become a little bit more complicated. So you're better off to learn this really well, in confidence interval and tests of significance, until we move on to chapters, to the future chapters that deals with two samples and also deals with the t-distribution. We'll talk about that too. So anyhow, so as I said, this is another type, and there are different names for tests of significance. Probably you've heard that it's called hypothesis test. It's called significant tests and tests of significance. These are the names that we use, basically. And so we are going to use exactly the similar assumption that we use for confidence interval, and we are going to do the basically use this for testing. Like for instance, an example is it's like someone might claim that, hey, when they say 12-ounce cans, the liquid inside the can, it's not 12 ounce. And it might be a little bit less or a little bit more. But if you average it out, probably average that he might claim or she might claim that it's 11.6 or 7 or 8 ounces. So that is the claim. So we can test that claim. Testing that claim, it's called, basically we can use test of significance and claim that test and see whether that person is right or wrong. That's it. That is the meaning of test of significance. Something is happening, it's in the norm. We assume that that is a norm. And someone comes along and claims that, no, that is not the result. I claim that the result should be greater than that, the norm, whatever the norm is, or less than whatever the norm is, or not equal to the norm, whatever the norm is. So based on that claim, we call that alternative testing. And based on that claim, we test that claim and whether we reject that claim or we fail to reject that claim. There are two cases. So the terminology is a little bit important here. So I'm going to go through these more, that how to use when we say reject the null hypothesis or fail to reject the null hypothesis. Those are the two sentences we use. Okay, let's just do this example, and then we move on to null hypothesis, and then we'll go through that too. You can see, because we are going to use it, this example, in the future, in the next slides or pages. Okay, here what we have. The phone company believes that smartphones which are compatible with a watch increase consumers' valuing of the phone. Phones which are not compatible with a watch on average are valued at $450. Assume that prices are normally distributed. Okay, so let's do this problem. I'm going to write the information. Let's look at the part A. Suppose we know sigma. This is the population, basically standard deviation. $108, that means suppose we know. It's not saying that we get this one from a sample. It says suppose we know. This is $108 for the distribution of prices for phones, and that the average price of all phones are $450. So basically, I'm going to rewrite it here a little bit. so you can see it. Sigma is $108, right? And then we have mu. It says the average price of all phones are $450. That again, this is for the population, $450. That is the average price. And SRS of 12 consumers values the watch compatible phone at the values listed below. Find X bar and label it on the graph X density curve, assuming mu is 450. So we took a sample of 12, and they claim that these are the prices. So in order to look at this price, I got to find the average price for this sample. The average price, if you recall that, we say average X bar is equal to, we add all these numbers divided by the total numbers that we have here, which is 12. So that means 480 plus 515 plus all the way to the end, you have 480 plus 445 divided by 12. If you do that, you get the value to be, this would be equal to, X bar would be equal to $513.75. That is based on the sample, the average price of compatible phones with watches, basically. Okay. So if we want to plot this, S now is sigma over square root of n. Sigma is 108, n is 12. And if you put these numbers there, it becomes something close to $31.18. Okay. Now, if you want to plot this one on normal, it says a normal distribution. This is mu. Mu was $450. And mu plus S that you have here, basically. So this would be the next standard deviation we have for this value. Here, this would be somewhere $481.18. All you're doing, you're adding 3118 to 450 average that we have. So is S for sample size and sigma for, yes. Yes, we always use for sigma for sigma, we use sigma for population, mu for population, X bar for X bar is for sample, and also we use S for the sample too. Okay. So you put the values here, that would become another one here. If you put 31 here, that is, where is my, the other one would be 512.36. The next one would be here, that would be $31, that would be $542. And 46, something like that. But that is the third one you have. But the important thing is our value, that our average lies here. That is $513, $513.75. That is there. It lies there. Okay. What they asked us to do, and this is it. Let's do part B. Part B, it says how probable is this sample value? That is, if mu is 450, that is the population mu, is really true, what is the probability that another sample mean would be found that is at least as extreme, or extreme means that as high or higher than the observed sample mean? So if I want to write this one, translate into formula, so it says, what is the probability? Let's read it from here. So this is what we have, 450. So it says, what is the probability that another sample, so the probability of another sample, X, this is the probability of another sample mean, would be found that is at least as extreme or as high as this one. So at least as high as uh, the mean that we had calculated here, as we are comparing this. So what is the probability of that? I can say at least to be this. Because here it says, if you look at how probable is this sample, we are working on this sample. So we want to take another sample, find the average of that sample. These are the average we are doing. This is the average for the new sample. We want to see how probable is the next sample. If we take it, 12 of them, we do the same calculation. How probable is it that mean of that sample is going to be greater than the mean of this sample we have? That's what you're trying to calculate. Again, if we want to do that, we use the usual thing. This is greater than sign, so we have to write 1 minus p x bar less than, what is it, 513.75. We have to calculate that. As you know, anytime you have it in X form, if you want to use the table, table has everything in Z format. So you got to convert X's to Z's. And you have to use Z-score. Z-score would be X bar minus mu divided by sigma over square root of n. Okay, so we want to say we use this one, 513.75 minus mu of the population is, what was it, 450. Sigma was 108 divided by square root of 12. Calculated this from here. This is 31.18 from previous calculation. So if we calculate, subtract this and divide it by that, Z becomes 2.045. Now we have to calculate the Z, P of Z less than 2.045. And that would be equal to 2.045. By now, you should know how to do these calculations, right? 2.045 So this is a 2.045. We're gonna look at it on the top here. We'll put it between these two. We'll either take this one or that one, either one, or in between, whatever you want to do. Take this 0.05. 2.04, 0.9, that would become 0.9738. 0.9793. I'm sorry, this would be 0.2 point. That's what we could see it. Okay, 0.9793. 0.9793. So this corresponds to this one when x is less than that. So if you want to find the entire thing, so you got to subtract from 1. 1 minus 0.9793. And this is equal to basically 0.0207. Or you can say 0.021. But from here you can say 2.1%. So all it based on what we have, if we take another sample of 12 of them, like the way we did it here, and we want to know that it's going to be as expensive as the average of these samples, or greater than that, what is the probability of that? Probability would be 2.1%. That's what we did here. Okay? Let's move on to, now this is the definitions for null hypothesis. Okay? The important thing is here, the null hypothesis, we usually show it by H0. You can see it here. It's the proposal that models the status quo. That means it looks at what's out there. It has no judgment on that, whatever that we are doing the measurements against. It assumes it's there, so we are going to take that value. So it is status quo or the conservative viewpoint. That's another one. Or you can use other stuff here. The case that you see no differences. Something that it's been there, it has no effect. We usually use equal sign for null hypothesis. Not usually, always we use equal sign. So you're going to see that. What else? What else? And here, the way we write it, we say null hypothesis H0 defined to be, we're talking about the average in terms of the average. Mu is going to be population mu because we are not saying that the population mean, which is mu0, is wrong. Someone is going to claim this and is going to come up with the alternative hypothesis and say, well, this is not the right thing. But in terms of the null hypothesis, we just assume that what is given to us, we are going to take it without questioning it. It's like you assume that, like in a criminal court, what we usually assume that what the defendant is innocent until proven guilty. H0 is the same thing. We assume that whatever it has there, the property has it, the kind of property that H0 has, the value it has, a conservative value, we have no judgment on this. We are going to take on the face value, whatever it is. And then when the alternative hypothesis, we'll do the testing against that, and either we reject it or we fail to reject this null hypothesis. That is the whole idea. So in this case, mu0 is $450. So again, what did they say that here? When they say that this is like the value $450, we accept that. We are not questioning that. Now, the alternative hypothesis, it's different. Alternative hypothesis, and remember, when we do this, in this case, we are going to use the alternative hypothesis. Either we are going to reject the null hypothesis or we are going to fail to reject the null hypothesis. Okay, those are the two ways of saying it. So the alternative hypothesis, H0, H sub A, it can be defined to be, someone might claim that, oh, no, the mu is greater than mu 0, or mu is less than mu 0, or mu is not equal to mu 0. Those are the three claims we can have. In the null hypothesis, we can only have the claim that it's equal. In the alternative hypothesis, you have three kinds of claims. Can you move page up for previous problem really quick? What's the previous problem? Okay. So what we have here is, the idea is between the null hypothesis and alternative hypothesis. Again, null hypothesis deals with the equal sign, mu is equal to mu 0. Alternative hypothesis picks one of these cases. Either it's greater than mu 0, less than mu 0, or not equal to mu 0. Okay? So, our job is to do the test. When we do the test, we either find evidence to reject the null hypothesis, say this is wrong, I am right, or fail to reject the null hypothesis, saying that I am wrong, this null hypothesis is right. So you use two sentences, two ways of saying this. Reject the null hypothesis or fail to reject the null hypothesis. So when you reject the null hypothesis, you accept alternative one, right? I don't want to write this. It's not the terminology that we use, but that's what it means. Reject the null hypothesis. If you reject that, that means your alternative hypothesis is correct. If you fail to reject the null hypothesis, that means the alternative hypothesis is not right. You have to accept the null hypothesis. Okay, now we have two different alternative hypothesis curves, and the mu. One is when you have mu is greater than mu 0. This is H sub A. And the other one is mu is less than mu 0. The first one, when we draw this, we draw the curve like this. This is, you're looking at, if the mu is like this, you're looking at this area. This is when mu is greater than mu 0. In this case, you're looking at this area when mu is less than mu 0. Okay? For this is called single value or one-sided, or it's called one tail. There's one tail. So this only happens either greater than or less than mu 0. The other one is alternative hypothesis when mu is not equal to mu 0. If it's not equal to mu 0, then there are two cases for that. If it's not equal to 0, then it's going to become two-tailed. This is called two-tailed. Two-tailed, tail, two-sided, and double value. And the reason we are going to use that, I'm going to show you something here, and this is the part that we are going to be interested in. We can see here, this is called one-sided P, and this is called two-sided P. Two-sided P deals with basically the alternative hypothesis when mu is not equal to mu 0. One-sided here deals with mu either greater than 0 or mu 0 or less than mu 0. That's one-sided, this is two-sided. The values that we calculate for P is going to be probability. We'll go through this, but that is the reason I just wanted to mention something here when you look at the table. One-sided versus double-sided. So in our case that we had here, H0, so our mu is equal to, mu 0 is 450, then the alternative hypothesis, H sub A, it's either one of these, it can't be both of them, either greater than $450 or less than $450 or not equal to $450. These two represent one-sided. This is only represent two-sided. Okay, for our example here. All right. Okay, the next thing is, the important thing is the p-value. You saw here, this is the p-value. Oops. So this p-value. This is one-sided p-value. We calculate this is the p-value. This is the row for the p-value. This is a two-sided p-value. We calculate it. All right, the p-value of the test is the probability. We said that it's a probability, assuming H0 is true. When you calculate p-value, the assumption is H0 is true. So that means if the p-value becomes as small as possible, that means you have less probability to accept H0, the null hypothesis. So if the probability is very small, another way of saying it, you reject the null hypothesis. If the probability becomes big, large, that means the probability of the null hypothesis, H0 being true, it's large. So that means you're going to accept H0 to be true because it has larger probability. Therefore, you have to reject the alternative hypothesis. Another way of saying it, you say you failed to reject null hypothesis. That means you're accepting the null hypothesis because P is large. So we are going to go through this, assuming H0 true, but all I'm saying, when you calculate the probability, in the back of your head, just you're thinking in terms of assuming that H0 is true. So if the probability is low, you're going to reject the null hypothesis. If the probability is high, you're going to fail to reject the null hypothesis. That is all. We would find the value of our test statistic more extreme than the observed one. That's what it is, basically. So let's go through this. This is example 2. So I'm going to rewrite, I'm going to write this one here to what I said about smaller p represents um, rejecting the null hypothesis. Larger p basically means that failing to reject the null hypothesis. So this is about the p-value. P-value. So the smaller the p-value, smaller p-value, basically stronger the evidence against H0. H0 is the same as saying null hypothesis. Provided by data. This is basically provided by looking at the data and making this decision. So if this happens, the conclusion is from here, you say reject the null hypothesis. So the smallest value is the best for the testing. Because if you claim that what you're doing, the testing that you're doing, it's going to be right. You are looking for smallest value of P to reject the null hypothesis. And opposite is true. If the opposite is true, that means if the p-value, the larger the p-value, the weaker evidence you have to against H0, and therefore you say fail to reject the null hypothesis. So for that one, I don't have enough room. Maybe I should do it here. Large p-value means fail to reject the null hypothesis. Okay. So basically, if you fail to reject the null hypothesis, that means whatever it is, you're going to accept it. Let's work on what we have here. In the previous example, it says state null and alternative hypothesis for the study in example 1, right? Then use the p-value to make a conclusion about whether or not the watch-compatible phones are considered to be more valuable than the non-watch compatible phones. Okay, so let's do that. Here, what we had here, let's look at this one. What we had here, this is 17 years. Okay, so what we had here, our mu zero is, remember, it was $450. So I'm going to accept that if they told me that here, phones which are not compatible with a watch on average are valued $450. This is what's given to me. I'm not arguing with that. I'm going to take that value, assume that that's my null hypothesis. So therefore, the null hypothesis is going to be, because I'm not going to change it, no effect, no difference, most conservative value, and it's given it to you, and then you're going to take it on the face value basis. So H0, it's going to be, your mu is going to be mu zero. That means it's going to be $450. That is the null. The alternative hypothesis claims that if we did the average, that's going to be greater than $450, right? So it says more expensive. It's going to be more expensive, right? Phone company believes their phone is compatible with the watch. Increase. You see that out? So you got to look for words in your problems: increase, decrease. Those are the signs that whether you have to take it greater than the average value or less than the average value. There are some indications that you can make this judgment when you read the problem. So in this case, the alternative hypothesis, mu has to be greater than $450. Okay, now I have this. If I didn't have this p-value, I had to go through this p-value and calculate this, right? But it's already calculated for this value for x bar, and everything is calculated. So my p-value is, based on what I have there, it is 0.021 or 2.1%. Okay, 0.21% is small. It's very small. Not very small, but that's small. Usually we accept anything between like a smallest value all the way up to 5%. And it depends on the experiment that you're doing. On the experiment that you're doing, maybe you can accept 10% too. It depends on what you're doing. In some experiments, hey, 5% is really huge. You put your limit as 2%. It depends on the experiment. This is, suppose you're going out, you gather the data, and you're analyzing the data, you're trying to do this test of significance. And when you do that, based on what you have done, you put your limit at, you say, well, I'm calculating the amount of this drug. You're working for a drug company that it's going to help people. And the smallest amount has really large effect. So in that case, you might you might decrease this one to even 1% or 2%. But for all practical purposes, for our class, we are going to assume that 5% is going to be our limit in this case. If it's greater than 5%, basically we are saying that probability is big. If it's less than 5%, we are going to assume that that probability is small. Okay? The limit depends on what you're doing. No, I don't have the exact equation. It depends on the kind of test that you do. Again, I mentioned that. But usually problems are, you're going to see that in the next statement here. So it's given the level of significance. It's given to you, and it's called alpha. And if it's not given to you, the assumption is you assume it's 5%. But if it's given to you, it depends on the experiments that you're doing. You got to follow that level of significance, which is alpha. We'll see that. But in this case, let's just go with this one and see what happens. The assumption is we are going to put our threshold at 5%. And if it's less than 5%, so we are going to say we're going to reject the null hypothesis because it's small. If it's greater than 5%, we are going to say it's big, it's large, so we can reject the null hypothesis. Based on what we have, 2.1% is less than 5%, and therefore we concluded that reject the null hypothesis. So if you reject the null hypothesis, what is it then? So that means you have compatible watch with phones. They are more expensive. They are great. It doesn't say how much expensive. All it says, it's greater than what you have in average, 450. Less than that, or different than that. That's all it says. When we do this testing, it does not give you the exact value. if we look at the whatever the average is or whatever the norm is, we put that one there. And if we claim it's greater than that, either we prove that to be greater than or not greater than. Based on that, we draw the conclusion and say either we reject it or fail to reject. Okay, in this case, we rejected this null hypothesis here. Null hypothesis. That means the watches are compatible watches with phones are more expensive. Basically, it's greater than the average. Okay, I can give you an example. Let's just let me just make it a little bit clear here that if you use that alpha, as I mentioned, here we have alpha. If the p-value of the test is less than or equal to alpha, we say the result is statistically significant at level alpha. Alpha is that percentage. Suppose, let me just give you an example here. Suppose the problem, this problem is giving me alpha should be 5%. Alpha is 5%. So in this case, if we calculated this, and this is for mu greater than $450, right? So we calculated this, we came up with 2.1, and 2.1 since is less than 5%, so we rejected the null hypothesis. Alternatively, I might say that, hey, the price is not, I don't know, I would say the price is different. I don't know, it's greater than or less than. If that is the case, and my alpha is still, say I put the alpha here to be 5%, again. No, let's see, it doesn't work with that. Let's just make here alpha the same experiment and say alpha is, it's given to us as 0.02 or 2%. Say if the statistically significant at level alpha to be 2%, assuming that's the case. If that is the case, then you have 0.021 is greater than 0.02, and then you say in this case, because you have alpha reference that you're referencing to alpha, you say not statistically significant and therefore you fail to reject HC. If that is the case, okay? Now, let's go with the procedures. How do we deal with this null hypothesis? I did not say what chapters are going to be on the exam. I have not made up my mind, and it might be chapter 18, it may not be there. I have no idea. Depends how far we are going to go through the chapters. But let's do this one. So this is a definition. The z-test for population mu, assuming normal distribution and known sigma. Pay attention to here, we say sigma is known. In the future, you're going to see some of these values are not known. Mu, mean, is not known, or sigma is not known. Then we deal with different kind of distribution. In this case, for one sample that we are dealing, we're assuming mu and everything is known. So you have to write both hypotheses. So that means null hypothesis and H sub A. That would be the alternative hypothesis. But you have to know what that is. Is it greater than null, than mu zero? Mu is greater than mu zero, mu is less than mu zero, or mu is not equal to mu zero. And then you have to find the test statistic. And this is the test statistics and z-score. calculate Z from here, and based on Z, you try to find p-value. So p-value, either it's going to be greater than or equal, less than or equal, or absolute value. Greater than or equal provides you with the mu to be greater than mu 0. So when you calculate the p-value for this, remember you always have to write p minus z, capital Z, less than or equal to smaller z. For this one, you write p capital Z less than or equal to z, smaller z. For that one, which is not equal, you take 2, multiply it by p of z, capital Z less than or equal to smaller z. Because this is a two-sided. In this case, you're doing this. This is greater than that. So basically, if you are calculating this, you take 1 minus this entire thing, and you calculate this area. In this one, you're calculating to the left of this. If this is the area, you're calculating to the left of this, which is okay. In the last one, when you have both, they're symmetric, basically. So you calculate one, which is going to be p of z less than this. You calculate this, then you multiply it by 2, then you cover these two. So that's the reason you're multiplying it by 2. So two-sided, two-tailed, and so forth and so on. So in general, so then after this, you make a conclusion. Either you reject the null hypothesis if the result is significant, or fail to reject null hypothesis otherwise. So that means it's significant. That means if your p is less than alpha is given, then you reject it if p greater than alpha otherwise. This is a curve in general. This is mu. Mu is not equal to mu 0, so therefore you have two tails here. One is going to be plus z, the other one is going to be minus. Therefore, you have this absolute value of z. We put it there. This is for h sub a. When you say z mathematically greater than absolute value of z, that means z at one point is minus z, at another point is plus z. Write the sheet down. Okay. Okay. Let's do another example. Okay. This is example 3. A 2009 study sought to determine if the response time of individuals who did not typically play video games was lowered by the act of training with games demanding quick responses. In the quoted tasks below, the researchers used the abbreviation NVGPs for non-video game players and RT for response time. This is what they did. In these training studies, 25 NVGP were randomly assigned to either an action game, Unreal Tournament, Call of Duty 2, or a control game, The Sims, which they played for 50 hours over 8 to 9 weeks between pre and post testing. Across the 4 tasks tested before and after the training, action game trainees demonstrated decrease in response time 7%. Decrease in response time, that means you can put minus 7%. That's decrease. Compared with the population. Okay. Now, let's assume that the standard deviation for response time is 18%. So I'm going to drop all the percentage, and sigma is 18. Okay. When compared to the population average, and that when they said 25 people played were assigned, they meant 25 to the control and 25 to the experimental group. So each was 25. N would be 25. Okay. And X bar, this is here what we have across the graph. This is the decrease that we have here. It's 7%, right? This is on the average minus 7. Okay, now is there evidence at 5%? This is alpha, it says it here. 5% level to support the claim that response time is decreased by training with these video games. Okay, so that means my alpha is 5% or 0.05. So it says here, is there an evidence at this level to claim that response time decreased by training? So decreased by training with the video game. So let's write, and this is part 2. So I'm going to do it this way. So the first one is we have H0. So we are comparing two groups that doing this. One is basically you're looking at the gamers and others that they are not playing, they haven't played. So basically, when I put mu is the difference between two people who, gamers and non-gamers, basically. They played a video before and they didn't. So we are comparing those. So I'm going to say mu is the difference. Mu is difference, the difference in response time in the gamers and others, not non-gamers. So therefore, I'm going to say if the difference is 0, remember we go with something that's null. We don't care what happened. What we take it, assuming that there's no difference between these two groups that they're playing this, gamers and non-gamers. So if there is no difference, that mu would be equal to 0. Another way of saying it, I can define this one to be, here I can show you, I mean, there are many ways we can write this. We can write mu is equal to mu gamers minus mu non-gamers, G, that is equal to 0. That means mu gamers are equal to mu non-gamers. The assumption is there is no difference between them. Instead of writing this, I wrote this one. You can write that too, either way. What does that say? M is the difference of mu. Okay. Yes, mu is the difference in response time. We are looking at the response time. This is a response time. Between gamers and non-gamers. Between those who played games and those who did not. NVGPs, that's what they call them, non-video game players, and those who play. The assumption we are comparing these two groups, one versus the other. So if we are comparing that, if you're looking at the null hypothesis should have any judgment, which one is better. So the assumption is both of them should be the same. That is the null hypothesis. No difference. Remember, no effect. You go with the status quo. You 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 don't change anything. You take everything on the face value, assuming both are the same. Assuming both are the same. Now the alternative hypothesis, it claims that when the trainees decrease their response time, right? We read it somewhere. Decrease the response time. After that, action trainees, the evidence 5% that response time is decreased by training with these video games. So that is the claim. So if that is the claim, I want to say decreased. That means it becomes less than 0. Another way of saying it, instead of doing this, you can say mu gamer minus mu non-gamer is less than 0. So gamer that they played game, or it's greater than, one is greater than the other one. That's the claim. Okay. So we are going to use a Z formula. Z is equal to basically x bar minus mu divided by sigma square root of n. So x bar, it says here that x bar is on the average -7. Here we assume that our mu is 0. The difference is 0. Your mu, this is the mu 0. It's 0. So 0, you put 0 there. Divided by 18, sigma is 18, and number of people participated in each one is 25. And if we do that, we get z equal to minus 1.94. It's 5, take it up and then divide it by 5. Because we have mu less than 0, it's less than sign. Therefore, if you want to calculate the probability, you say probability of z less than minus 1.94. So you don't have to subtract it. So subtract this one from 1. So all you have to do, look at minus 1.94 and find the probability for that. And we use this one now. Here what we have, this is minus 1.9, minus 1.9, minus 1.9, minus 1.94, minus 1.94, minus 1.9, and that's 4, and this would be, that would be, what? It would be minus 1.94, that would be 0.0262, 0.0262, 0.026. So we got the probability. Now it says we are dealing with this at alpha level of 5%, right? So let's see, 0.0262 is less than 0.05, isn't it? It is, right? So because of that, we say the smaller this value is compared to that, you say evidence gets stronger and stronger. There is a strong evidence to reject null hypothesis. H0. Another way of saying it, this is what you have. This is minus 1.94. Z. Okay, let's do the other part quickly. So now the next one, it says here, what if the question is whether or not response time is different after training? It does not say less than or greater than. It says different. So if you want to write the null hypothesis, everything is going to be the same. Now the null hypothesis, H0, still is going to be mu equal to 0. And alternative would be mu is not equal to 0, because it's whether or not it's different. It says different. It doesn't specify that whether it's greater than or less than that. So if that is the case, if you want to draw this curve, so basically this is going to be minus 9.194. This would be 1.94. So that means if you calculate this area, because of the two tail, because of this, you have two tails, so you have to multiply it by 2. So the p-value in this case, p-value would be 2 times basically what we calculated previously, 0.0262. And if you calculate that, if you multiply that, you get 0.0524. And we know that 0.0524 is greater than 0.05. This is the alpha value. Because this is greater than that, we say fail to reject null hypothesis. So you see what happens when you have different values, because you have to calculate for two areas, and we did this, and you can see here in this case we failed to reject it. In the previous case we actually rejected and accepted the null hypothesis. All right, this is page 3. We have one more page to go. So there's no questions. Good. All right. This is example 4. And example 4, we are dealing with, it says, already. Well, I guess it's 120, yes. All right, I'll finish this on Wednesday. And most likely, chapter 18 is going to be on the midterm too, second midterm, most likely. We'll find out on Wednesday. All right, if you don't have any question, I'm going to sign off and have a good day, good afternoon, and I'll see you guys on Wednesday. Yeah. Thank you. Bye.